let's revisit the boom problem one last time. And so in this boom problem, we're going to have our boom be at an angle, right? And I showed you that before in that introductory video where I had that black stick, there it was, and there was a rope attached to it at some point, okay? And then there was a weight hanging off the edge, okay? So generally in these sort of problems, usually we're trying to find the tension in this rope as well as the pivot forces. So let's go ahead there and we'll approach this just from an analytical standpoint, and then we'll do a problem with numbers. So what do I have here? Assuming that this is a uniform boom, I'm going to have the weight of the boom acting down halfway. So FGB, there it is. Let's say the boom is L long, okay? There we go. And we're going to have the weight of this, whatever this is, Fg of the mass, M. We're going to have a tension acting there, okay? I'm going to draw in some sort of angle there. I'm going to call that theta B for theta of the boom. And I'm going to say that here is some sort of theta T, which is the angle the tension is making with the boom itself. All right, so I think it's probably pretty logical. We're going to use X and Y. So once again, I'll put in my boom pivot forces, FPX, and I'm going to guess FPY. I have no idea. So remember, we're just going to guess those. And I'm going to put the pivot there so no one cares about that. Let's say that that object is attached at 0.8 L up. So we need to have that distance drawn in there. And obviously then this is at 0.5 up because it's at the geographical center. So I have all my distances labeled. All right, so axes and declarations. Now, there are some people who will say, okay, well, maybe we should tilt the axes. I'm not a fan, and here's why. If I tilt the axes, then like pretty much everything has components there, and that just is going to get ugly. So I'm just going to leave everything in normal X and Y, right? And there it is, which means that the only thing I really need to put in components for are Tx and Ty. So there we go, Tx and Ty. And that's what the free body diagram looks like. So, oh dear, what is this angle now? Well, that angle, if you look at the way that this is, alternate interior angles are equal, it looks like this is theta T minus theta B, and so that's going to be a pain in the ass later, but there it is. So let's do what the easy work is. Sum of forces in the X is equal to MAX. We know that that's going to go away, and so then that's just FPX minus TX is equal to 0, or FPX is equal to T cosine of whatever that theta T minus theta B is. That's fine enough. I'll just leave some space there in case I need that. Sum of forces in the Y is equal to MAY. I've got TY plus FPY minus FGB minus FGM, right? Or once again, T sine of theta T minus theta B plus FPY is equal to MB plus M quantity G. Nothing very interesting there. But things get a bit more interesting when we go to construct the torque equation. So here we go. I'm just going to construct that down here. Sum of torque is equal to about that pivot I alpha. And so let's look at what produces a torque here. Well, the two pivot forces won't, but the two weights will, and both components will. So what do we do? Well, we're just going to go, well, what's producing positive versus negative torque? Ty, positive Tx, positive Fgb, negative Fgm, negative. So I'm going to have a positive torque due to Tx plus a torque due to Ty minus a torque due to B minus a torque due to M equals 0. So a couple of things there. someone's going to say, and rightfully so, couldn't we just do one torque due to the tension? The answer is yes, and I'm going to show you an alternate solution in a couple of minutes about that, and it's up to you to choose what you would like to do. Okay, and we'll see how we'll approach that. But here, I'm just going to keep this like this so that I can show you sort of a uniform methodology. And then if you'd like to do riffs or variations in the theme, of course, you are allowed. So here we go. Force times lever arm. Easy enough. I'm just going to put the forces in. So this is T cosine of, once again, that theta T minus theta B. And this is going to be T sine theta T minus theta B. This is just going to be FGB. And this is going to be FGM. Okay? That's what I've got so far. Now lever arm distances, and this is where this problem really comes to play. So lever arm distances. Remember, it's the perpendicular distance between the axis of rotation and the line of action of the force. So for Tx, if I look at this, that's the line of action of the force. So since it's a horizontal line, the force, the lever arm distance must be vertical, which is this here. And so I'm looking for this, which is this length times the sine of this angle, which is theta b. So if you look at that, that's going to be 0.8 L times the sine of theta b. Okay, right? Horizontal distance, or rather horizontal force, vertical distance. And for Ty, here's my line of action. That must mean I am looking for this horizontal distance. So that's 0.8 L cosine theta b. So for FGB, once again, that's this distance here. So that's 0.5 L cosine theta b. And then for FGM, right, vertical force, horizontal distance, that's just going to be L cosine theta b. And from here, it's just pretty straightforward in terms if I knew numbers for these things, just to plug in and solve for the algebra. Now you might be distressed by this geometry here, but nothing really to do except for just work it out. Now, I do want to show you that alternate solution, what happens if I didn't want to consider the two components. Now the components were helpful for the x and y equations here, but not as helpful for the torque equation. So yes, you could have done sum of torques is equal to 0 and just done plus the torque done by the tension minus the torque due to FGB minus the torque due to FGM, and just said, well, if it's the entire tension force, what I would really want to do here is our other version of the torque equation. Remember, torque is equal to force times lever arm, or torque magnitude of torque is equal to FR sine of theta, right? We're going to use that FR sine of theta analysis here. So it's just tension. R here is just how far it is, which is 0.8 L, and then the sine of some angle. Now, the angle is the angle between R and T when drawn concurrently. So I'm just going to do a little drawing up here. And so there is T. And when drawn concurrently, R looks like that. So it is not this angle here, but it looks to be this obtuse angle right here. So what's that obtuse angle? Well, we know here that this is theta T. And so this has to be 180 minus theta t. And so this is the sine of 180 minus theta t. Okay, and then minus, and all the other stuff is going to be the same in the other one, but that is a simpler expression maybe than all of this is. I don't know, my brain just operates better doing the components since I need components for this analysis here. But that's the way that these boom problems go with the angles. Right, and that boom can be angled in all sorts of different ways. There's different ways that it can be supported, but like that's the general idea of it. So in the next video, it's totally optional. You can try the homework if that felt comfortable to you, but I'm gonna work my way through problem 44 in the text with some numbers so you can see a worked problem happening.